Hi, welcome to this class. This is Physics 892, many-body problem. So uh, this course is about physical principle and mathematical formalism. So if you think about quantum mechanics, in fact, in quantum mechanics, what we call the physics is very much related to calculational tools. Uh, so if you think of the wave function, it's a complex number, and it's a function of, let's say, position, the three coordinates of one particle, the three coordinates of another particle, and so on and so forth. So it is defined on a space that grows exponentially with the number of particles. So if I just give you the wave function, well, what's the physics in this for when there are many particles? Well, yeah, you don't know. It's not very transparent. So instead, as we do usually in quantum mechanics, uh, we will concentrate ourselves on observables. So let me share my screen. So for example, an example of observable is the expectation value of the number of particles at a given point. And by this double bracket, I mean quantum mechanical and thermal average. Or you can look at higher order correlation functions. For example, if there's a particle at a given position, let's say, let me write this a little slightly differently, n at position r, n, then this is a correlation between density at one point and density at another point. But in quantum mechanics, we don't have just bilinear observables like the density psi dagger psi. We also have amplitudes. So another type of correlation function is just psi of t psi dagger, for example, where you correlate the amplitude of something happening at a given time and particle being somewhere else at a different time. So this type of correlation function is called a Green's function, and that will be one of the objects that will interest us in this course. Now, I want to stress that, again, that if we think of what is the physics is very much in perturbation theory, in a sense that when we think of particles colliding and so on, and there are many particles, we may want to write some collision between two particles. But this is just a way of making pictures for perturbation theory. But there will be not only perturbation theory, but there will be some more general concept that will emerge. Like, for example, the concept of a self-energy that I will call sigma, and that is the analogous to viscosity, if you want. Or, so this is a self-energy. And this, for example, is another concept which would be the vertex, which represents scattering amplitude or what happens in the collisions. And these two objects, self-energy and vertex, will be objects where we will hide, in a sense, our ignorance, in the sense that instead of knowing the whole wave function, we will know objects that are smaller, more related to observations. And these objects, self-energy and vertex, are places where you will see why. I mean, it's a bit like viscosity, where we can hide some of our ignorance when it's time to do approximations. So the the images that I draw here, for example, are intimately related to the formalism. So in this class, we will sort of need to do at the same time the formalism and the picture, the images. We sort of develop the two aspects together, like it's done usually in physics. That's not very unusual. And there are a number of books on this subject. I will come back to what are the books a little bit later. But what we are doing is developing a language in the sense. I mean, there's this concept of self-energy, of vertex, of Green's function. Another concept will be the concept of spectral weight, and some rules. So there are not that many actually. Not that many concepts in some sense. I mean, we will come back over and over again and try to understand what they mean more and more deeply as we go on. Now, in this context of perturbation theory, the contribution of Feynman, who invented the diagrams that I'm putting there, were very, very influential because, because they helped, I don't know why it's doing this. They helped understand or make strides in quantum electrodynamics and provide us with the most accurately known or calculated number in all of physics, the gyromagnetic ratio of the electron. But nowadays, we do need to go beyond perturbation theory. And in that case, the formalism that is better adapted to that is the formalism of Schwinger, who earned a Nobel Prize. I'm sorry, thinking to write at the same time as I. Okay, Schwinger, okay, who shared the Nobel Prize with Feynman and with Tomonaga for the quantum electrodynamics. So we will be, it's very, in the lecture notes that you will be using, the two formalisms are developed independently. But in fact, it's hard to do both of them at the same time. So I will mostly emphasize the Schwinger formalism, which is more closely related to algebraic approach. But it's also possible to make pictures with the Schwinger formalism. So I will make pictures with the Schwinger formalism, and so we will have both the pictures and the algebra. So as you will see in the lecture notes, there are many subtle points in addition to these main concepts I'm discussing. And these subtle points they are in remarks in the lecture notes. So it's more like more advanced topics or things that require a little bit more thinking I will turn this off. A little bit more thinking to know what is going on. So the two very important ideas that we will develop is that of adiabatic continuity and broken symmetry. So what do I mean by that? So adiabatic continuity is basically a statement of perturbation theory or a statement of a phase of matter. Suppose you look at a metal. You have seen in statistical mechanics that you can just fill energy levels all the way to the Fermi level. And that gives you a metal, and the electrons are not interacting. If you add interactions, what happens? Well, it turns out the metal stays a metal, and the electron is replaced by a quasi-particle. This quasi-particle has an effective mass. It has some damping if it's not exactly at the Fermi surface and temperature is not exactly zero. But is basically adiabatically connected, in other words, by perturbation theory, to this non-interacting problem. So very often the main properties of a phase can be understood by simple models that are adiabatically connected to the exact solution of the problem. There will be a broken symmetry. I'll come back to broken symmetry in 1 second. In this context of adiabatic continuity, there will be two main models we will study. One is the Coulomb gas, and the other one is the Hubbard model. So the Coulomb gas will allow us to understand the screening, and the Hubbard model will allow us to understand, for example, Mott transition, ferromagnetism, and in fact, even some ideas about high temperature superconductivity. Now, what about this idea of broken symmetry? What happens is that sometimes you start to do perturbation theory in a phase, or you have some phase that you assume is well described by some non-interacting Hamiltonian. And then you say, okay, but in reality, I know there are interactions, so you put them back. And then you see that perturbation theory diverges at some temperature, for example, or some value of the coupling constant of the interaction. So what happens if the perturbation theory diverges at that point? It means you cannot go to larger interactions, or you cannot go to lower temperature, let's say. So perturbation theory breaks down. So there's a phase transition. The self-energy, the free energy that you know, has some singularities. And you cannot go beyond that point. So in that case,
I'm sorry, I have a question.
Yes, please ask questions. I forgot to insist on
that. Do you mean by that within our model we cannot go beyond that temperature, or do you mean that physically we cannot go beyond that temperature? I mean, suppose I have a material, and I know that when I had those perturbation and those interaction, now it diverges. Do you mean that our model cannot simulate those materials, or do you mean by that this material cannot go beyond a certain below a certain temperature?
No, the material can go below.
Okay, so it's just our models that breaks down.
It is just that you have a phase transition. You have a new phase, and that phase is not adiabatically connected to the original phase you started with. It cannot be described just by perturbation theory. Let me give you an example that will help.
Okay.
So, example of broken symmetry. So first, before you break the symmetry, suppose you're in a normal metal where there's as many up and down electrons, okay? And then you decrease the temperature and you find out that because of interactions, at some point you start to favor up spins. Okay, there can still be some down spins, but there are more up spins than down spin. So you have broken a symmetry, okay? Because before there was as many up as there were down spins. Now there are more up spins. So the rotation symmetry you had at the beginning is broken. You have an up spin. Is that okay? Do you understand this? Yes. So we will see that superconductivity is another great example of broken symmetry. It's a bit more difficult to understand, but so what to do when that happens? Should we give up? Well, then what you do in the case of the ferromagnetic case, it's easy to know what to do. Instead of starting with the Hamiltonian that is perfectly rotationally invariant. In the Hamiltonian, you put more up spins than down spins, and you don't assume that there are as many up as down spins. Okay, so you break the symmetry by end if you want. And then to study that phase which has more up spins than down spins, you can use adiabatic continuity. You can start from this non-interacting Hamiltonian that has more upspin than downspin, and then add the interactions and see what happens with these interactions. And what you will find out is that, again, perturbation, let's suppose that this is interaction strength here. And let's suppose that that's the paramagnetic phase, and that's the ordered phase. So here I do perturbation theory, and whoops, it diverges here, so I cannot go past this point. I start with a new Hamiltonian that breaks the symmetry, and then I can use adiabatic continuity on that side. You see what I mean?
Yeah. Okay. Thank you.
So that's don't assume that you're supposed to understand everything at this point, right? I'm just giving you some general ideas. So the BCS theory of superconductivity will be like that. We will sort of guess what the Hamiltonian should be in the superconducting state, and proceed from there.
Just another question on the same topic. So when we say the broken symmetry, that we break it by end at first, it's not something that we, like a spontaneous broken symmetry that happen in our systems. We will really need to change the model at the beginning, that to express those things.
Yeah, the way this in the normal, let's say in the paramagnetic state, the system responds to external perturbation in a certain way, okay? And what will signal this phase transition will be that, for example, the magnetic susceptibility, which is just a way of saying how does the system magnetize if I apply a small magnetic field, the magnetic susceptibility will diverge. So it's telling you that it wants to order. You see what I mean?
Yeah, yeah. Okay.
So if it's a first order transition, and you know about first order transitions also, then all bets are off. It's very hard to guess what the other phase will be. But if it's a broken symmetry phase that comes in continuously, then usually it is signaled by, in this simple way, that there is some response function that starts to diverge, and that tells you, that suggests to you what Hamiltonian you should write down for this other phase.
Okay, thanks.
Okay, so so this idea of broken symmetry is a little bit in this general framework of a famous paper that was written by P.W. Anderson that's called More is Different. And we need to have this sort of framework where we can see properties of a system that emerge from having many of them. I will give you an example in one moment, but let me tell you why it is difficult to do. I said you have to guess the Hamiltonian. I showed you ways that perhaps you can guess what it is, but let me just give you in one word one of the problems with if we want to do everything from scratch. If you start from atoms, the energy scales, as you know, are 10 eV for the hydrogen atom, and then you have hundreds of eV or kilo electron volts if you include all the electrons for atoms. But if we're interested in something that the phase transition that occurs at 10 Kelvin or something like that, you're talking about milli electron volts instead of hundreds or thousands of electron volts. So if you want to do because we know the Hamiltonian, we know the exact Hamiltonian for this system, right? You can write the Dirac equation. We know the Coulomb forces and everything. But if you want to do everything from first principles, you need accuracies that are incredible, 10 to the sixth or more. So in many body systems, there are things that are emergent, like superconductivity is an emergent phenomenon. Ferromagnetism is an emergent phenomenon. But you know what emergence is because you have encountered it before. What is entropy? You know what entropy is. You've done statistical mechanics. But the entropy doesn't mean anything for one particle. What is irreversibility? Irreversibility is something that emerges when you have many particles. Even temperature, absolute temperature is an emergent phenomenon, right? It's related to derivatives of the entropy. So absolute temperature is another example of emergent phenomena. So in the case of, let me take a simplest example from solid state physics. If you start from an aluminum atom, okay, an aluminum atom has a discrete spectrum, right? If you send light, it's absorbed only at certain frequencies. And you have a minimum frequency to go from the ground state to the first excited state. Now put a lot of aluminum atoms together and make a metal. It has changed completely now. It can absorb energy at arbitrarily small energy because it conducts electricity, right? So you can go at very low frequency and it will respond and it will absorb radiation. So what has happened? You have created a Fermi surface. So the Fermi surface in itself is an emergent phenomenon. And once you start to talk about Fermi surface and band structures and so on, there's another emergent phenomenon which is related to the topology of these band structures. I mean, the Brillouin zone is a torus, and you can go around this torus a certain number of times, or you can make finite cycles. And on that torus, you're carrying a vector, which is the wave function, if you have more than one band, let's say. Or let's say the spin is not degenerate. So that leads to topological properties. We will not talk about this topological properties in this course, except perhaps at the very end, advanced topics. I may show you that Green's functions can tell you about topology as well. For now, I'm just talking about emergent phenomena. So the existence of phonons, I mean, phonons are also emergent. I mean, the properties of if you just look at one nucleus or one atom, you don't know what a phonon is. So broken symmetries lead us to states of matter that are different, like a superconductor, like an antiferromagnet, like a nematic quasi-crystal or a nematic crystal or whatever. And each of these broken symmetry states have new particles. For example, in a ferromagnet, you will have spin waves. An antiferromagnet have different type of spin waves. So in a sense, every one of these new broken symmetry states are a new universe. If you think of our universe, we have electrons, photons, quarks. But in these broken symmetry states, the elementary particles are different. So that's one of the interests of condensed matter physics, or quantum materials as we call it. So let me end this introduction with a few more quick remarks. Despite what I said regarding the fact that it's very hard to do things from first principles, it's becoming more and more possible to have very good approximations from first principles. But there are certain materials where these first principles methods that are based on dynamical mean field theory, density functional theory, DFT, they are not enough to describe the system. So the density functional theory is basically mapping the problem on a non-interacting system. And I'm simplifying, but in the sense that. But when there are interactions, well, I mean, it has this failures. So some of the modern methods are based on density functional theory, which I will explain what that is, and on dynamical mean field theory. So in this class, in this course, we will do mostly model Hamiltonians. And that's one of the applications of model Hamiltonian. It's non-perturbative. I mean, you cannot use perturbation theory to derive dynamical mean field theory. That's an approach that goes beyond perturbation theory. And there will be other approaches, one that's called two-particle self-consistent, that we will also describe. So the idea of model Hamiltonians that I said we will use, these simple Hamiltonians that are not the exact Hamiltonian, but that have all the features that we that we need. The advantage is that they help us to understand the physics, and also they are soluble. So quantum mechanics is hard with us because it has exponentially large Hilbert space, but it's also kind with us because there's a separation of energy scales. For example, what quarks and gluons are doing in the proton will not influence the property. I mean, they will have negligible influence of properties you observe at room temperature. Similarly, there are energies. There are excited states that are so high in energy that we can sort of fold them back, sort of treat them and put all their effect in an effective Hamiltonian. So, I mean, there are classical examples of effective Hamiltonian. If you think of hydrodynamics, this, it has viscosity and stuff like that, and describes all sorts of liquids. The only difference is the viscosity, if you want, between all these liquids. So hydrodynamics is an example of a classical theory that is effective. In quantum mechanics, there's something similar, and it's even more justified than in classical mechanics because of the separation of energy scales, like I was saying. So I talked about the Schwinger formalism and the Feynman formalism. There's also the functional integral formalism. So there's sort of like three different formalism, each of which has its advantage and its disadvantages. And ideally, you should master all of them, but in practice, it's very hard to practice to master all of them. And they're all equivalent. There's no one that is more fundamental than the other. Although people could argue, I mean, there are some arguments in favor of functional integrals, but I won't get into this. That's again related to topology. The point I want to make is that, and that's a point made by Feynman, that the point that I want to make, that there's no formalism that is the best or the only one, is that it's a difference between the Greek and the Babylonian way of doing mathematics. So the Greeks, with Euclid, if you want, they start with axioms and then everything else follows. The Babylonians, they knew all sorts of different theorems that started from different point of views, and they managed to do mathematics this way. So in that sense, we should be like the Babylonian. Sometimes it's good. It's easier to start from functional integral. Sometimes it's easier to start with Schwinger formalism. Sometimes it's easier to start with the Feynman formalism. So in this course, we are learning, as I said, the physics, but we are also learning a language. And it's the language that's behind the calculations, behind the interpretation of experiments. And it's, in the sense, behind the workings of nature. Sometimes it will look a little bit like if you're learning spelling and grammar, right? But at the same time as you learn spelling and grammar, you start to be able to read interesting stories. So I think it's a little bit this way that I see this course, this class, is that you're building the rules or the alphabet, or if you want, the language that will help read these great stories and write your own stories. Okay. So if I go to more prosaic considerations, I will go very quickly through the plan de cours, so the course outline. But before I do that, I was just to mention regarding, mathematics, so or prerequisites. So if you have done statistical mechanics, if you have done quantum mechanics, you have the prerequisites, undergraduate course, I mean. As far as mathematics, what I would recommend is to review Fourier integrals, the convolution theorem, Fourier series. I will come back to these. I will remind you of all of this, but that's something that we will use all the time because we will use translational invariance, basically. And the other piece of mathematics that I would recommend you to look back at, and again, I will remind you of all of this, is the residue theorem in complex variables, how to do integrals in the complex plane and how you can do that by looking at the residue, Cauchy theorem, for example. So you see there's not that much mathematics. In principle, this is all mathematics that you know. It is, we will just build on that and then develop some new mathematics, but then fundamentally they're all based on these concepts. Okay, any questions before I go to the course outline? Okay. So, there it is. So, you can, I mean, the office is irrelevant here, but you can contact, whoops, I'm not sharing, right? I should be sharing, just a second. Okay, you see this? This is the course outline.
Yeah.
So you can contact me by email. The person will grade the homeworks is Chloe. I will introduce her, I think, to you perhaps next time. What I want to point out here is that it's a 3-credit class, 3-credit courses, and it means 3 hours of in-person meeting and 7 hours of personal work. And I will tell you how to spend, so excuse me, if you look at that, it's like 2 hours per course, per class. So I will tell you how to spend these 2 hours. You will see in a moment. So everything is in the, I mean, on Moodle, you have the link to the lecture notes and so on. So I don't think we need to go through this because you've seen, I will let you read sort of the general objectives and the specific objectives. I think I've mentioned that already. What I want to spend a few minutes on is the evaluation. So 50% of the grade will go into the following. So after each class, you will look at the lecture notes that I will bring up here in a moment. So the link, there's a link on the Moodle page to these lecture notes. And I will do roughly, 10 pages roughly per hour. And you see it's rather dilute. I mean, it's not like extremely dense pages. But what I want you to do is to go through the derivations. But I will be using this light board from now on. But it's not so convenient in the sense that it's not very big and it takes forever to erase. So what I will be able to do is to explain to you, what are the main points, why it's important, what it means physically, how it's related to what precedes, how it's related to what follows. And I will do the proofs that I can. Some of the proofs are very long, but they are done in much detail in the lecture notes. So what you will do then is after each class, you will go through the lecture notes and write the derivations, at least those. Perhaps you don't need to write every derivation, but those that are non-trivial, you need to write them up. It can be done in a rough way. It's your own work. And then what you do is that you send your notes to Chloe. And if you hand in these notes that show that you have read the course and you have done the calculations, you get the full grades for that. She won't look at details. Perhaps she will give you half of the grade if it's clearly deficient. But for the first few times, we will not put any grade. We will just tell you, is it really what we want or not? Okay, so I want it will be clear for every one of you if it's satisfactory or not, or how you should do that differently. Okay, so basically, if you just follow the course and go through the lecture notes, make the derivations, you already have 50% of the points. Then there will be 20% for homework, but there will not be many homeworks, and they will be very much spread out. So you spend most of your time on this. The homeworks will be graded correctly, and the final exam will be 30%. Okay. So I don't think it's particularly difficult to make this class. I mean, we are in a pandemic, and it has to be a little bit special. So basically, if you work regularly, you already have 50% of the grades. And if you manage to do half of the homeworks, you have 60%, and you fail the exam, you're almost right. Okay. You see, I mean, I wanted some sort of minimum for the final, but
just to be sure.
Yeah.
So there's no midterm.
No midterm. No.
Okay.
Good point. Yeah.
Okay. Thank you.
Okay. So there's 5 minutes remaining. So let me, excuse me, go through the outline very quickly. So here this 2, for example, means chapter 2, and this is chapter 3. So let's look at the notes. So you see 3 is susceptibility, propagator, some general properties. So 3 is susceptibility, quelques propriétés générales. Okay. So these numbers here refer to chapters in the lecture notes. So the first part we start with the classical harmonic oscillator. And what I want to do there is to do the harmonic oscillator in a way that's different from what you have done before, because what I want to do is introduce concepts of frequency-dependent damping, irreversibility, and causality relation, Kramer-Skirting, and introduce the notion of susceptibility and so on. In other words, there are many things that we do for many-body problem that in reality are not specific to many-body problem. It's just that we don't refer to these methods very often in the other context, but they are very general. I mean, the concept of dissipation, of irreversibility, and how it's related to the infinite size limit, and the Kramer-Skirting relation are just related to causality. So I want to introduce all these notions within the harmonic oscillator. So that's done in the first week. So at the end of the week, I hope we are done with this. Then part 2 is on correlation functions and sort of their general properties. And now, like in any physical theory, what I'm starting with is, what do we measure? And we will see that in a scattering experiment, when you send some light and look at what's coming out, what we are measuring is fluctuations, a certain type of correlation function that's called fluctuation. When you apply a voltage and you measure resistance, it's a response function. And sort of every experiment that, or traditional at least experiments in condensed matter physics enter in one of these two categories. And there is a fluctuation dissipation theorem. In other words, these two quantities, the fluctuations and the dissipation, if you want like the resistance in one case and the scattering in the other case, are related by a theorem. So here in this part, what we see are these correlation function. You see Kramer-Skirting. Spectral representation is another concept we introduce right away in this simple example. And the fluctuation dissipation theorem. Lyman representation is something else we will hear about and later, and it comes in this simple complex context. Now, then third week is the response functions. So we talk in more detail about conductivity, what is the difference between a metal and insulator and a superconductor from the point of view of correlation function. And then I will introduce Green's functions from the point of view of Schrödinger's equation, the one-body Schrödinger equation. So that will be a very simple concept, a simple way to introduce Green's function. Then we start to generalize to the many-body case. And for the many-body case is where we need second quantization. So you don't need to know second quantization. I will introduce it in week 4. Okay, at this point, so here we understood, we start with part 4, which is Green's functions. And when we see this general structure of perturbation theory, it will be natural to introduce Green's functions in imaginary time. So which imaginary time is something very simple. It's normally the evolution operator is e to the I. So I is meaning minus square root of -1, Hamiltonian times time. And in statistical mechanics, it's minus beta times h. Okay, so beta plays the role of an imaginary time. That's all there is. And this will allow us to introduce a Green's function. The Green's function will have periodicity properties analogous to those of correlation function that I will describe earlier. And then we go to the Coulomb gas. So the Coulomb gas is very important to understand, for example, screening. Excuse me. So the electron gas is a rather long chapter where we introduce the random phase approximation, the Hartree-Fock approximation, concept of Lindart function, which is just one kind of response function. And then we also introduce this method of that is very useful in the case of first principles calculation. Then we move to our second model, which is the Hubbard model. And this is where we talk about metal insulator transition introduced by interactions. So random phase approximation, two particle self-consistent approach. But before we go into this more sophisticated thing of the Mott transition, I studied the Hubbard model like the electron gas. So we sort of make the analogy. We use the same type of formalism, if you want. And then that allows us to see the Anderson, the dynamical mean field theory I was talking to you about, and the Mott transition. Mott transition being this metal insulator induced phase transition induced by interactions. Then if I have time, I will spend a little bit of time on coherent state and functional integrals. So this is just formalism at the end. More importantly, this is where we start the broken symmetry. So we go to week 11, that's pretty late. So I begin to I introduce the broken symmetry and associated concepts like Goldstone modes is one type of excitation that one finds when the symmetry that's broken is continuous. And the so-called Merman-Wagner theorem, which are the important concepts. Then we'll spend a week on another broken symmetry, which is superconductivity, where we look at within the Schwinger formalism again, and the susceptibility that's diverging instead of being magnetic susceptibility is a pair susceptibility. And finally, the 13-week is completely optional. I mean, the 13-week will not be the subject of exam. There won't be homework for the 13 weeks. So I will describe just some advanced topics. So it's for those of you who are interested, I will go into this Luttinger-Ward functional and how to have a gauge invariant or conserving approximations, and Luttinger theorem and a various number of theories. So for the course, I mean, there's no book, there's just these lecture notes. But just to mention the better known books, there's Mahan, Quantum Theory of Many Particle Systems, and Fetter and Waleshka, and Abrikosov, Gorkov, and Zedoshinsky. These are classic texts. They're pretty old, but they are still very good. Another book I will use a lot is Foster, Hydrodynamic Fluctuations, Broken Symmetries, and Correlation Functions. So the first part, if you want, of the course is very much using that book. And in the new books that have come out more recently, okay, Kazaf and Bain I will also use here. And for path integrals, this book by Negeli and Orland is the best, I would say, or at least the one I know, which is okay, for recent interesting books, there's this book by Piers Colban, which is very, very physical. I mean, he doesn't stress he skips a lot of the mathematics and perhaps is, but the physical discussion is really excellent, and the range of topics is phenomenal. And then another one that I know my students like a lot is Bruce and and Flensburg. Then there are some free lecture notes on the net. So I know I went very quickly through this, but anyway, since this is recorded, you can always go and look at these brief comments I made. For those who are interested in quantum field theory and more generally, there's this book by Anthony Z, which is also excellent, very, very pleasant to read, but you probably need to know a little bit the topic before starting. It looks easy, but because some of the mathematics are done rather quickly. Okay, so sorry I spoke a lot. Next time, usually with this board, I need to split the course in two, so you get a little break in the middle. I know that listening for an hour on Zoom is not so fun, but I thank you for coming and for taking this class. Is there any question that comes up at this point?
Yeah, I have a technical question. So for the note that we do for the evaluation, so we send it to Chloe.
Yes.
We send is there some place on the Moodle that we
yes
where we send it by email?
Yes, you can send it through Moodle. Okay. So next, I don't know. Well, I will check what's the best way to do that. I will discuss this with Chloe, what she will suggest. But yeah. Okay. So for the notes, as I say, I want them. So if I give a class on Monday, then on the next class is on Wednesday. So on Wednesday morning, you need to have, I need to know that you have not this class. I mean, you don't need to know anything about the class today. So, but Wednesday there will be a class, regular class. So when we come on Friday, I want you to have done what I just said. You go through the chapters and you write down the equations and you do the derivations. And I understand there may be, I mean, if you have a good reason not to do it, I mean, there's some urgency or you have some important homework or something serious, you have some debt in your family. But one of my friend was saying, after 4 of your grandparents have died, the 5th one, I start to doubt that it's a good excuse. But yeah, I mean, I understand it's not always possible. And let's say you don't need an excuse if you just give it one week. I mean, if you wait 2 instead of doing really the next class, you wait at the second class. You don't need an excuse, but please don't do that very often, because I really want you to be on track all the time. Otherwise, you will be lost very quickly. Yeah, but sure. If you do what I'm saying, I think it's very easy to follow this class. It's no problem.
And on the same way, do we scan it or a picture of the notes?
You can take a picture. You can just use your cell phone, or if you can scan it, it's even better because it makes more compact documents. There's an app that's called, I think, Tiny. What is it called? Tiny Scan or something like that. Tiny Scanner. Yeah, Tiny Scanner. You can find the app. I don't know if it's available for Android, but there will be the equivalent. There are a few apps that allow you to take a picture and which will make small files instead of sending 1 megabyte per page. It's not really convenient, and it doesn't help you to read. I mean, yeah. So you scan or you take pictures and send them together. If you take pictures, please, if it's possible, to use some software that puts all of them together so that Chloe doesn't get 5 pages for every one of you. It's easier to manage. Good. Other questions?
Well, it's not a question, but well, right now my camera is on so that you can see us and we can more easily interact. But if a certain amount of people start to put their videos and I just open mine too, I start to lag out. So if there's still two more students and everyone is sharing their camera, I'm not sure if I'll lag out or not.
Okay.
So, well,
Usually this is a Zoom is very efficient with bandwidth. So usually it takes like at the worst it takes 2 megabit per second.
oh, I should be okay then.
So if you have a 5 megabit connection, it will do it, even if you have many pictures, because each picture is smaller.
Mm.
So everything is done at the level of the server, if you want.
Mm.
And that's something I forgot to tell is that I have two computers. So on one of the computers there will be you, and the other computer is the one that will be used for the
Recording.
film to record and film the equations and everything. So yeah, I would appreciate if you leave your camera open, because I do see you all the time, and seeing you helps me keep more motivated, if you want. And I can see how you react and see, okay, wow, this is difficult, I need to slow down or something. If I'm just talking to 5 close cameras, it's not pleasant for me, and it's not pleasant for you, in the sense that I will be less reactive.
Mm-hmm.
So if you leave your camera open, I see you and you ask questions, and to ask a question, the easiest is to use the space bar. If you just push the space bar, it unmutes you. So when you release the space bar, it mutes you again. So that's a way to very quickly come in. You don't let me go. Just if there's something you don't understand, press the space bar and say, excuse me, and then you ask your question. I prefer that, and I'm sure that everybody else prefers that, because if you have a question, usually there are more other people that have a question also. And I gave you an outline of the class. That's really what I want to cover, but there's nothing that, there's no course that follows that one. So if I don't need to cover everything, if I cannot cover everything, it's not dramatic, like somebody else, I think his Weisskopf was saying, it's better to uncover a little than to cover a lot. Okay, I don't want to cover a lot of material that won't be understood. Instead, I want to uncover, in other words, that you see what's happening and that you understand. So I will adjust to what your rhythm. There's a minimum I really would like to cover, and I think I'm able to do it, but there are some parts I can skip without affecting the rest and so on, because it's as you will see, I mean, the lecture notes have 700 pages. I'm doing 10 pages per class, and there are 39 classes. So if I even cover 36 classes, so if I cover half of the lecture notes, I would be very happy. I mean, probably I won't be able to do that even. Okay, more questions? Okay, if not, thanks again, and see you on Wednesday morning.
See you. Thank you.
Thank you. Bye-bye.